Our next project is the digital ruler that uses a salvaged CD-ROM spindle motor as displacement sensor. It's not secret to anyone that any commutator DC motor is also a generator. However, the type of current such motor will produce is not exactly direct, because the windings are constantly switched by the commutator, thanks to which the circuit is periodically broken at a frequency proportional to shaft rotation speed. This is the feature that our device will rely on. You can see the schematic diagram on the screen. We will also use a 2-digit 7-segment display operating in dynamic mode. Just like in our previous sketches, data will be read with the analog input, but with a little nuance. It would be nice to implement counting in both directions, up and down, the way it happens in a digital caliper, for example. We know that change of rotation direction will cause change of EMF polarity on motor's output. How can we read this with the help of ADC? We can use a resistor divider and shift ground level to have the power supply voltage. In this case, motor's positive EMF will increase the voltage, while negative one will decrease it. But we would like our circuit to stay as simple as possible. So what are we going to do? We will wire the motor between two analog inputs and no resistors. As we already know, ADC in Arduino can turn into digital outs. So what we're going to do is switch one analog in to digital mode and set it to logic 0 while we read the ADC value of the other one. Then we just switch them. This will effectively flip the input polarity of the ADC. The main loop of the sketch is before us. The minus button is used to reset the counter. We switch the A1 input into digital mode and set it to 0. Then we read data from input A0. If the value is greater than 0, we increment the distance counter. In the next section, inputs A0 and A1 are switched. A0 is now zeroed and A1 is read data from. Based on the result, the distance counter is decremented. While experimenting, I found that faster motor rotation yields greater signal amplitude, which also affects the readings. To rule out this error, I introduced a calibration factor found empirically. The accuracy of the measurement can be adjusted using this constant. Let's check it out. Good.